Okay, Jenny, are you ready?
Yeah, I'm ready.
Great.
Okay.
Take it away.
Hello, everyone. My name is Jennifer Hernandez, and I will be one of the three presenters for today's presentation. So I, along with Braden Vanderall, who is our Change Board Director, and Daniel Roberts, our Chief Project Engineer, will be presenting the last, but definitely not the least, human-powered vehicle. Here we have our mission statement. The 2020 to 2021 CSUN human-powered vehicle team will be working together with limited resources during an unpredictable climate to develop and manufacture a competitive, yet safe, sustainable, and reliable vehicle, while simultaneously building a sound foundation for a successful career in industry. So we are fortunate every year, year after year, to have Professor Kachaturian be our faculty advisor as listed on this slide. And as you can see, the HPV team has been divided into 5 sub-teams: systems and integration and testing, frame, components, fairing, and innovation. So the names highlighted in black are the fall spring students, and the names highlighted in white are the spring fall students.
Hello, everybody. This is Daniel Roberts, and I'll be doing a brief overview of the vehicle. So we started with a 3-wheeled tadpole semi-recumbent rear wheel drive that had a steel frame, and then our fairing was a little bit different than previous years. We used a carbon fiber frame with Oratech 600 fabric stretched over it, and then our innovation was also a little bit different. We used an adjustable seat instead of a static seat. And then our overall vehicle weight came out to 52.68 pounds as designed. Now moving on to budgeting, we started with $23,300 and we are currently left with $14,400, and that amount is in the cash box and AS agency, so that will carry over into next year's team. And then in the chart above, you can see what each individual sub-team requested and then what they spent. Now, you can also see that we received several donations, $1,000 in cash. We fundraised by selling masks and last year's t-shirts. And then we also received high density foam, epoxy, and many bike components. This year we did a top-down assembly method where we had each individual sub-team create their sub-assemblies and then send them to us, where we could mate them together and then check for interferences, both static and dynamic interferences. And then we also ran calculations such as braking performance, weight distribution, and tipping angles. This led us to then calculate the center of gravity, where in order to achieve that performance that we wanted, we determined an envelope that we wanted to fall within, and then the actual, and so the actual with the fairing and without the fairing both fell within that range. We also, this year, as opposed to other years, tracked how the CG would change when the seat would be adjusted based on the heights of different riders. Lastly, we did a penetrant inspection this year. So many of you from Rocketdyne might know Richard Stiff. I was able to get him out and help us do some visible dye inspection and UV inspection. And so in figures 1 and 2, you can see the red dye we would put on the weld and then spray some developer on it and then clean it off. And then you can see the red indications in figure 2, where we have some cases of entrapment here in cold lap. The same thing is happening with the UV inspection in figures 3 and 4. However, we would have to shine the UV light on there. And then we found one crack here in the boom. And I'm now going to pass it on to Braden to talk about the frame.
How's it going, everyone? My name is Braden. So the frame team began with a 3D sketch that they modeled in SolidWorks. They incorporated a rollover protection system, which was required by ASME standards for the competition. The 3D sketch used our coordinate system, which started at the center of the back wheel so that we could hang all of the components and everything that was going to be attached to the frame in the top-down assembly like a Christmas tree. And there was various tubes, tube diameters that were used, all with 0.065 inch thick wall thickness as shown in the right. When they moved on to analysis, the frame team ran a finite element analysis on several different conditions. Some were self-imposed. 2 of them, the top load and the side load, were required by ASME competition standards. And we're happy to say that the frame passed all loading scenarios with a minimum factor of safety of 1.5. So they were able to continue on to manufacturing. For the frame manufacturing, it began with the tubes going to the CSUN machine shop to be roughly cut to length and bent. Any of the tubes that needed to be bent were bent by the CSUN machine shop. Once that was completed, it was taken off-site where the tubes were notched to the correct diameter that they needed and then welded. The welding was completed in a welding fixture using 3D printed parts to hold the fixture together. So the tubes were held in by those 3D printed parts, and then it was tack welded with a TIG before being welded with a MIG welder completely. The innovation for this year was our seat. We decided to make a movable seat as a team. The reason why, in years past, the seat was part of the frame and it was always going to be in one fixed location. So they would use these thick foam pads to kind of change between different rider heights. And it became very cumbersome trying to do this. So we decided, after riding previous vehicles from previous years, that the seat was just a big problem that we would have to address. So we came up with this innovation, which is to move the seat. It has several different components. You have the seat, the gas spring that actually, when you push a button, moves the seat forward and then locks in, and then the V bracket at the bottom, as you see. They ran FEA analysis on the V bracket, which is what attaches to the frame, to make sure that the weight of the rider would not bend anything, that the steel that was made out of it would be totally fine. And the final factor of safety was 3.7, so it was well within acceptable range. And then they did a couple, dirty tests with a poor man's method, since we didn't have access to everything, where we built a rig together so that we could test the gas pistons and the linear bearings. We found that the 20-pound piston deflected a lot more than the 60-pound, and thus it was kind of ruled out, and we used the 60-pound on the bike, but that the linear bearings held 280 pounds and they rolled completely fine. So the manufacturing, they decided to use the frame that had already been completed kind of as the welding fixture. So they put it back into the fixture that was used for the frame, and then placed the pieces that had been machined out from the CSUN machine shop into the fixture or onto the frame. And then the tubes were cut, specifically because the frame was slightly tweaked. It wasn't exactly perfect. So they were custom cut and tack welded before being taken off and fully welded off of the vehicle. And as far as the competition, so this year ASME had an innovation competition, which they haven't done in a few years. So they had an E-Fest just last month where we competed. We presented a report, a several-page report of what we did on the innovation before then presenting it to a live panel. And we're happy to say we got 4th out of 59 teams internationally. So we're very proud of our innovation team. And I'll pass it back to Jenny. Jenny, you're muted.
Sorry about that. So here we have an overview of the components configuration. Highlighted in blue, we have the steering, the braking, and the drivetrain system. So as a team, a decision was made to make the steering system indirect. As you can see in figure 2, there is a screenshot of the steering system. The handlebars connect with the steering rods, which then connect to the knuckles, which finally connect to the Ackerman arm. This then ties in both the left and the right wheels. We also decided to mount a mechanical disc brake based on our specific goals and real life scenarios, and a chain drive was selected rather than a belt or a shaft drive system due to its ease for serviceability. By choosing these configurations, we were able to meet the goals listed on the right side of the slide. For analysis, we use finite element analysis, and it was performed on various components. But however, on this slide, we have in figure 1, we have the left knuckle. Figure 2, we have the kingpin, and figure 3, we have the idler bracket. And so we analyze the von Mises stress, displacement, and yield strength. So boundary conditions were established to analyze real-life scenarios, as previously mentioned. And of course, it was crucial that deformation was not a big factor when forces were applied. When it comes to manufacturing, the team designed with manufacturing in mind, definitely. Usually, we are able to have more face-to-face with the machinists at CSUN. However, this year, due to the pandemic, that was not a possibility. So what we had, the plan we had was to have the drawing submitted to Professor Cacciatorians. The machinist Caesar and Neil also were able to give us some input, and then before actually finalizing drawings. So this definitely helped out with production time and just reducing the possibility of rework. Of course, we included GD&T into our drawings to ensure proper fit functionality between components, such as figure 1, which is the kingpin and the knuckles assembled as one.
Now I'll finish it off with talking about the fairing. So our fairing, as previously mentioned, decided to do something very different. So instead of doing a full body carbon fiber layup, they decided to do carbon fiber tubing frames and then assemble them as panels and then assemble them that way. So they had 2 options depending upon which competition we'd be competing in. So one would be to have the nose cone and the partial fairing, or the windshield or top panel, as you can see. And then we would also have a full fairing, which would then be with the addition of those side panels on there. Now, of course, we had to analyze this. We used a 30-mile-an-hour velocity to analyze it, and with a 1.98 frontal normal force, we were able to trim the contour and really streamline this process to get the coefficient of drag under 0.1, which was a very big improvement for our team, especially for a completely new design. As far as manufacturing goes, these carbon fiber tubes were cut to size, then they were inserted into 3D printed joints and glued together with epoxy. And then those panels were then assembled together. And you can see in the left photo, the middle left photo, that David is using a heat gun to heat shrink that Oratex 600 onto those panels. And this is then the end of our presentation. And so on the next slide, you can see the finished full fairing with NARG sitting in there and all of our attachment clips and windows all assembled on there. And then the photo on the right then shows without the fairing and without the seat. So now I'd like to open it up to the panel for any questions.
Yeah, congratulations on the well placing at the digital competition. My question is, you mentioned that the seat added more weight. Why was that allowed when generally the overall goal is to have as lower weight as possible?
Great question. We were okay with a little bit of extra weight because this was a completely new innovation that had never been done before on CSUN, HPV, or other teams. So they're in the beginning stages, and over the years, if they choose to continue this, could streamline it. So material choices could be improved for sure, and design could also be improved. But Braden, do you have anything to add to that?
Yeah, and the other thing that we talked about as a team is we know that we want to get the bike as light as possible when we go to competition normally. Now, given that we knew it was going to be fully online and we couldn't actually ride to compete like we would normally have to, we decided, why don't we try something new since they're doing an innovation competition and see if what we can do to help, future year teams basically.
Okay, thank you.
We have two questions from Professor Bichet. So the first one is about the safety factor that you guys are considering. So is 1.5 acceptable for the application that you guys are considering?
For the frame, I believe. Is that referring to the frame?
He has, yeah, I would say.
Okay, so yeah, that is well within the what ASME requires of us. So over the years, over many years of competition, we always try and put requirements that are stricter than ASME gives us. That's we can look back at components goals that they set, and those are much stricter than the ASME guidelines, and the same as with frame for the deflection and the load.
Okay, so that's okay. So he's saying that's more general. So for like it was reported multiple times. So we're talking about different components, not only the frame. So is it acceptable for? So in general, is 1.5 like under the limitations that, or at least the
Yeah.
rules that there's? Okay.
Yes, some of our innovation had a 3.7 factor of safety, and our components you can see is 1.5, and frame was between 1.5 and 2.2. So we're all above 1.5.
The second question he has is about the smoothness of the fairing. So if you compare it to last year's design, so what are the effects that you? So did you account for the effects, like in terms of aerodynamics, like drag, or general like performance?
Yeah, we did several different revisions and remodelings of the fairing. We trimmed the contour a lot. It was a lot wider, and we made that tail very thin, and then the height we were able to bring a lot closer to the roll protection system, which is this upper corner on top to protect your head. So we were able to bring that down, and that significantly lowered the coefficient of drag. And then we also narrowed the nose cone to be able to streamline that as well. So I cannot speak to last year. I'm not sure exactly how it performed, but as compared to last year, but I know that several revisions were made, and we significantly streamlined it to what you see here. So.
Okay. Right. I would like to thank you, thank the team, so the human powered vehicle, for the presentation, and everybody for the questions.